Now we're going to get into 2D a little more and look at more shapes. So we're not dealing now with this lines that continue on forever, angles which continue on forever. We're dealing with closed solid shapes. And so that's what a polygon is. A polygon is a closed figure in a plane determined by at least 3 straight lines. So I have some examples of polygons for you. You need 3 straight lines to close in a figure. And so you can see there are 3 points where these lines meet. Another example, you can have kind of a house-looking shape. Not going to be perfect, but that's fine. And so you have 5 lines that form this closed shape. I can draw something even funkier like this. This also has 5 lines that form that shape. The lines aren't forced to be the same. The angles aren't forced to be the same. Just lines meeting each other. Okay. These points that I've highlighted are where the lines or sides meet. So the points where 2 sides meet is called a vertex. Or you're going to hear vertices for plural. Okay. So this would be a side, a side, a side, vertex, vertex, vertex. Okay. So it has 3 vertices on this shape. Now, if we do have a really nice shape where every side is the same length and all of these angles are exactly the same, it's called a regular polygon. Like here, those angles aren't the same for everything. Likewise here, they're completely different. So they're just called polygons. A regular polygon is still a polygon where all sides are the same length and all interior angles have the same measure. Now, based on the number of sides, we have names for those types of polygons. I'm only going to go through a few, and I can fit it on this page, so that's good. Some of them you're used to, but these are the most general term I can give that object. And then for some of them, I can give you a picture. Other ones, not so much. If we have 3 sides, that's going to be our triangle. And so looks something like that. If it's regular, all of them are the same, but it doesn't have to be. 4 sides, you might think of a rectangle, but it's not more generally called that. It's called a quadrilateral. So quad meaning 4. So that would be 4 sides, square, rectangle, that kind of stuff. 5 sides is a pentagon. So like the pentagon in DC has, I think, 5 like components to it that forms. So we want to do a 5-sided shape, which is basically a house. 6 sides is a hexagon. That's 1, 2, 3, 4, 5, 6. 7 sides is a heptagon. Okay. Can't really draw that one too nicely. 8 sides we can do, it's an octagon. And so that is our stop sign. You're used to that. See that probably every time you drive your car or drive somewhere. 9 sides is called a nonagon. Definitely not drawing that. 10 is a decagon. Just kidding, we don't care about 11. 12 sides is a dodecagon, kind of like a dozen. And then 20 sides is the last one. It's an icosagon. Obviously, there's more, but these are kind of the main phrases. You definitely will know these ones. 12 and 20 can't really visualize that so much. You can think of like a D20 for an icosagon though. But now, how do I know what angles these have to equal? So turns out every 5-sided shape is going to have the same sum for those interior angles. Every 6-sided shape has the same sum of those interior angles. But I don't know necessarily what that's going to equal just yet. So pretty much the last thing we're going to do today is come up with this formula for if I have a 5-sided figure, what is the sum of those measures going to be? Okay, and then maybe we'll do one example. We'll see how long it takes. So we want to figure out, how do we know how much the interior angles should add up to? To do that, let's think of a triangle. Doesn't need to be regular. It can be whatever shape you want. I've got angle 1, angle 2, angle 3 here. And I want to see what is the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. What we're going to do is extend these sides. So I extend the side between 2 and 3 a bit. Then I'm going to draw another line through angle 1 that's parallel to this one. Okay. So line 1 is parallel to line 2. Okay. And then I'm going to go ahead and extend these sides of my triangle out further. So I got one side extended, another side extended. And we are going to really use those special angles from last time, or 5 minutes ago, really. Angle 2 is going to be the measure of this angle up here as well, because these are alternate interior. And likewise, over here, angle 3 is going to be the same as this angle here, because they are also alternate interior. So these 3 angles actually form a straight line. So in a triangle, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is going to be 180 degrees. Okay. In a right triangle, or regular triangle, each angle measure is the same, so the measure of angle 1 plus, measure of angle 1 is equal to the measure of angle 2, which is equal to the measure of angle 3. In total, it has to be 180 degrees, but there's 3 of them, so each angle has to be 60 degrees. So in general, the sum of the interior angles for a triangle must be 180 degrees. So every single triangle, the angles are going to add up to 180. Okay. Now what if I change the shape? What about a quadrilateral? Okay, that's a four-sided figure. Could be square in shape, might not be. See if this, nope, doesn't want to go nice and straight. Let's see. There we go. Four-sided figure. Well, if I cut this in two sides, I see triangle 1, which has 180 degrees for these. And then I see triangle 2 here. And these angles have to be 180 degrees. So for a quadrilateral, there are two triangles. So the measure of the interior angles must be 2 times 180 degrees, which means they have to add up to 360 degrees. Okay. Let's try one more shape. We'll bump it up one more side. Let's look at a pentagon. That is a five-sided figure. Okay. And let's count the number of triangles that I fit in. So connecting those two sides gives me one triangle. Connecting these sides gives me 2. So in total, I have 3 times 180, which means the angles must be 540. If I do a six-sided polygon, it's going to have 4 triangles. So the sum of the measures of the interior angles of an n-sided polygon is the number of sides minus 2 times 180 degrees. Okay. So you can kind of see that this is a 5-sided figure, 3. 4-sided figure, 2. 3-sided figure has 1 triangle in it. Okay. So with that, we're going to jump into an example to start. And it tells us a stop sign is the shape of a regular octagon. We're going to determine first, A, the measure of an interior angle. So I'm going to go ahead and do the best to draw my octagon. Let's see if it will recognize as an octagon. Nope. Let's try it one more time. There we go. Close enough. Not perfect. Do my best to make it somewhat nice. But all these in theory should have the same side length and the same angles. So when we talk about an interior angle, that basically means one of these angles here. I'll call it X. We want to figure out how many degrees this is. What I do know is I know the sums of every angle. Okay, so the total sum of the interior angles is the number of sides, which is 8, minus 2 times 180 degrees. So it's 6 times 180 degrees. My total sum is going to be 1,080 degrees. Okay, but they tell us it's regular, So every side length is the same. So a single interior angle of a regular octagon is this total sum divided by the number of angles there are, or each one would be 135 degrees. So that's what we called angle X. The measurement of angle X is going to be 135 degrees. Okay. For the second part, we want the measure of exterior angle which we're going to call 1. So this one, your book does provide a picture. So here is our regular octagon. Don't need this anymore. Angle 1 would be this angle right in here. So that's our exterior angle. Okay. I don't know what that is, but I do know that this is 135 degrees from the previous part. So the measure of angle 1 plus this 135 degrees forms a straight line, so this better equal 180. So to solve for the measure of angle 1, we go ahead and subtract 135 degrees from both sides. And that tells us the measure of this angle is going to be 45 degrees. Okay. All right. So what we have left really are now going to be to talk about something called similar figures. And we also want to talk about special types of triangles and quadrilaterals. So quadrilaterals, really when you think of a four-sided figure, it's probably more common for you to jump in and say a square or a rectangle, but those are special types. Same with triangles. We have a ton of different types. Okay. The first one is an acute triangle. So what you'll see here is all of the angles being acute, so they're less than 90 degrees. Second special type is an obtuse triangle. And this means there is one angle that's going to be obtuse. I can't have two, because that would be two angles that are more than 90 degrees. And that breaks the rule of them adding up to 180. So here, only one angle is obtuse. Oh, and my pen went wacko. There we go. Third special type is one we have already seen, which is a right triangle. And so one angle is a right angle. So one angle is 90 degrees. So it has that little box in it to tell us that. Next, we have an isosceles triangle. And so isosceles, you have two sides that are equal to each other. Let's see if I can, doesn't want to auto make my triangle. There we go. So here, these two sides are exactly the same. And so those little tick marks indicate this. It indicates which sides are equal. Okay. So in isosceles, two sides are equal. But also the angles across from them are equal. So these two angles would be equal. We got two more types. Next one is equilateral. And this is where all of the sides are the same. So really it's a regular triangle. So every side is the same length and every angle is going to be the same. So all sides are equal and all angles are equal. And they're each going to be 60 degrees. And then finally, if it's really not special at all, nothing is the same, it's called a scalene triangle. So here, every side is different, every angle is different. So no sides or angles are equal. Okay. So based on the picture that you see, you're going to indicate, or you're going to see a ton of these tick marks. You can have multiple classifications. So technically an equilateral is an acute triangle because all of the angles are acute in that case. You can have a scalene triangle that's obtuse. You can have a bunch of things. You can have a scalene triangle that's a right triangle as well. So there is overlap between these. So when you're asked to identify the type of triangle, you want to be as specific as you possibly can. Okay. So we'll look at this one first. It tells us these two sides are equal and these angles are equal. So because those two sides are equal, it's definitely isosceles. And also, none of these angles are more than 90 degrees. So it's isosceles and it's acute. Okay. If I change this diagram slightly, and I still say these two sides are equal, this is also isosceles, but now I've got this large angle here that's definitely more than 90. It's isosceles and obtuse. Okay. And finally, if I have this picture, if it wants to make a triangle, that would be great. There we go. And I just know that this angle is 90 degrees, but no sides are the same otherwise. This is right and scalene. Okay. All right. So this leads into our special kind of classification for figures. If I give side lengths to something and I go ahead and just blow this triangle up much bigger to like 2 times its size, well, that's not going to change the angles at all. They're still going to be the same. It's just going to stretch the side lengths by some factor. So when that happens, we say that figures are similar. So two figures are similar if their corresponding angles have the same measure and lengths and the lengths of their corresponding sides are proportional. So the angles do not change at all. The sides get scaled up or scaled down by the same factor. So I'm going to show you an example. Here's my triangle, not drawn to scale, of course. There we go, that looks good, sure. And I'm going to call this triangle A, B, C. This side is 1, 2, 3. We are told this angle is 100, this angle is 50, and that forces this angle to be 30, so they add up to 180. If I go ahead and really just duplicate this, let's stretch it. Now it's twice as big, roughly. Those angles do not change at all. Okay. But now I've got new side lengths. So this gets bumped up to 2, this gets bumped up to 6, this gets bumped up to 4. And we'll call this DEF. Okay. So triangles ABC and triangle DEF have the same angles. So they are similar. Okay. And the thing you can notice is triangle DEF is twice in length to triangle ABC. Okay. So if I go ahead and look at side AC and I connect the side between the 50 and 100 degree angle, 2 times the length. If I look at the side connecting the 50 and 30 on each triangle, 2 times the length. And then if I connect the 130, 2 times the length. So those sides correspond to each other. Okay. So kind of looking at any ratio, if I put side length AC over side length DF, it would be 1 in the top, 2 in the bottom. If we look at side BC and EF, also going to be 3 over 6 or 1/2. And finally, if I look at side AB and DE, so I'm keeping the same triangles in the same position, that would be 2 over 4. All of these are exactly the same. They simplify to 1/2. Okay. So because of that, these are called corresponding pairs because they're the corresponding sides of those triangles. Okay. And so we'll do another example in a minute. Do I want to do, sorry, debating whether I want to do my special type of quadrilateral, but now we'll go through another example now. Given the similar figures, we're going to find the following. Okay. First thing I'm going to do is draw our figure. Close enough. And this is side A, B, C, D. I'm going to go ahead and duplicate it, and we're going to stretch it a tiny bit. I'm going to call this side A prime, B prime, C prime, D prime. We're told this is 9, this is 6, this is Y, this is 15, this is 10, and this is X. This angle is 80 degrees. This angle is 70 degrees. This one is 80, and this one is 100. First thing we're going to do is we're going to find the measurement of angle ABC. Okay. And that's going to be this angle right here. So if I know this angle, then I can go ahead and use my formula to figure out that those interior angles must equal 360. But really, because these are similar, these two should be the same. So this should also be 100 degrees. So the measurement of angle BCD is equal to 100 degrees by the other figure, or the other quadrilateral. Okay. Now that I know that one's 100, I can go ahead and use the fact that it has to equal 360. Okay. So a quadrilateral has interior angles that sum to measure 360 degrees. So the measurement of this last unknown ADC is 360 degrees minus the 80, the 70, and the 100 that are in that figure. So in total, this angle has to be 110. Okay. And then immediately you can fill in these other shapes if you want. This one also has to be 110. And this one has to be the same as B over here. So that one also has to be 70. Do you need to? No. But this way we have it. Okay. Now, the second thing we want to do is a little more complicated. We want to find the value of X. And so that's this last remaining side here. If I compare it, its corresponding side in this figure is going to be 6. Okay. What I need to do is I have an unknown. I've got to utilize this idea somehow. Okay. If I look at my figure, side AB is corresponding to side A prime B prime. But I can't tell you right off the top of my head what that scaling factor is. It's not like I'm multiplying by 2 or by 3. I'm going from 9 to 15, and I can't do that multiplication as readily in my head. So instead, what we're going to do is we're going to set up some type of ratio. Now, the reason I didn't use these two sides is although I know 10 over here, I don't know this side length there. So I don't want to use those. So instead, we're going to note that if I take side AB and divide it by its like figure on the other side, which is A prime B prime, it better equal my corresponding sides over here, which is side BC to side B prime C prime. Okay. So filling in those pieces, side AB is 9, A prime B prime is 15, BC is 6, and our unknown side is X. So basically, I have to solve this equation for X. Well, I definitely don't like these fractions, so let's go ahead and cross multiply. And that gives us 9 times X is equal to 15 times 6. So that's 9 times X is equal to 90. And so to solve for X, you go ahead and divide by 9 to undo the multiplication between those two. And our unknown side is 10. So this side here is actually equal to 10. Okay. Okay. So this leads to our last special definition between figures. We've got similar, which is that scaled up version. You can also have congruent. So that basically means they're exactly the same shape. Sides haven't changed, angles haven't changed. You might have just kind of rotated this thing on its edge. So if the corresponding sides of two similar figures are the same length, the figures are called congruent figures. Okay. So let's look at an example. We're going to find the length of the remaining sides and measures of the remaining angles for the congruent triangles just triangle ABC and triangle A prime, B prime, C prime. Definitely not drawn to scale. Here's A, B, C. Duplicate this, and we're gonna go ahead and just rotate it a bit. Try not to change it. There we go. A prime, B prime, C prime. We are told this side is 34, this side is 18, this angle is 31 degrees. This angle is 78, and this side is 33. So I'm going to go ahead and start with the angles before I do the sides. These match up with each other. So that prime indicates that it's the side or angle corresponding to it. So right off the get-go, angle B is 78 because B prime is 78. So the measurement of angle B is 78 degrees. Likewise, angle C is 31. So C prime has to be 31. Now to find this last angle, which is the same as angle A prime, the measurement of angle A is the same as A prime. In total, it has to be 180. So I'm going to go ahead and subtract the two angles we have, the 31 degrees and the 78 degrees. So this angle has to be 71. Okay. Now I need to turn to our side lengths instead. So connecting A and C gives you 34. Let's go ahead and make that a little bit bigger. A and C gives us 34. So A prime, C prime should also give us 34. So side AC is equal to A prime, C prime. They are both 34. Okay. Moving on, what color haven't I used? We haven't used orange. AB is the same as A prime, B prime. So they both better equal 18 since they're congruent. So AB is A prime, B prime. They're both 18. And then one last side, connecting C and B, C prime, B prime. They both better equal 33. Okay. So when they're congruent, it's definitely much nicer than if they're just symmetric because you've got a lot more work. Okay. You really kind of just get to match things up, find the other side. So we're going to spend a lot more time with all of these shapes in the next section because we're going to talk about finding areas and finding volumes very soon in the future too. So we're going to work with them quite a bit. So the last thing I really have is just, again, more definitions because I know you're not definitioned out by this point. But it's similar to kind of the triangles. We have special types of quadrilaterals. So a lot of verbiage really going on. But luckily there's not as many for quadrilaterals. In total, we have 5 special ones. First special one is a trapezoid. And so for a trapezoid, you're going to have 2 sides that run parallel. They don't need to be the same length. And then these other 2 sides just kind of do whatever they want. So I tend to like to put little arrows to indicate that they're parallel. Nothing told about the angles, it's just 2 sides are parallel to each other. Now, if I want all 4 sides to be parallel, that is called a parallelogram. Again, nothing about the angles, nothing about what those have to measure. But these 2 sides run parallel and they're going to be equal to each other. And likewise, these other 2 sides run parallel and they're going to be equal in length. So both pairs of opposite sides are parallel and both pairs are equal in length. Kind of long definition. Okay. So parallelogram indicates the sides opposite of each other are parallel. But let's see if I can kind of stretch this or edit this. It's not the best. I don't want it to get confused with our next definition. So you can have two really long sides, two really short sides. These are in parallel. These are in parallel, and they're the same in length. If I want all sides to be exactly the same length, that is what's known as a rhombus. Okay. Don't want it to look like a square because that's another special type. There we go. Okay. So for a rhombus, these two sides are parallel. Likewise, the left and right are parallel. So a rhombus is a parallelogram. So bad at spelling. Parallel, that's not parallel. It's like, that doesn't look right. Parallelogram. So it is a parallelogram, but all sides are equal in length. So these four sides all have exactly the same length. Okay. And finally, we've got two special ones, which you probably know their names. A rectangle is a special quadrilateral in that it is a parallelogram because these sides are parallel, these sides are parallel as well, but every single angle in these corners is going to be 90 degrees. So the angles are the same, which isn't the truth here. These two angles will be the same, these two angles will be the same, but that's the only guarantee you have. So for a rectangle is also a parallelogram, but all angles or all interior angles are 90 degrees. And then finally, we have our favorite one, which is a square, in that all four sides are the same in length. They run parallel to each other, and these angles are 90 degrees. So this is our regular polygon for four sides. But more precisely, a square is a rhombus. So all sides are equal in length and parallel, but all interior angles are 90 degrees. Okay. So you're going to have to recognize a lot of these shapes just in your homework. It's going to give you an image. It's going to give markings on it of some sort, and you have to go ahead and figure out what is that specifically going to be.